Oh, 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. And let's see, how did we do? Varieties. So it's asking us to find work done by, or let's say the network, sign of network, or is it 0? So we got positive, negative, and 0. Okay. So let's suppose I am thinking A as correct answer. Am I right or wrong? And why? Am I right or wrong? Why?
Professor?
Yes.
I had supposed that it was positive due to the fact that the angle between the force of the electric field and the displacement of the particle is 0 degrees. So cosine of 0 is 1.
Cosine 0 is positive 1. That's right. Okay. So that means force, displacement, and cosine. And in this case, force, we are calculating about the work done by push force here, the work done by our hand, right? Or push force, whatever it is, right? And cosine 0 degree. So that's displacement and that's the force angle between them. So cosine 0 is positive 1. Okay. So what do you think, folks?
I was confused because I thought force was going to be a negative magnitude because it's being forced into a direction that the charge doesn't want to go.
Okay. So force was this way. So it is getting pushed. And where is that force coming from? Electric one, right? The charge is pushing it down. And if that was the case, then that would be theta would be 180 degree, means negative work. Cosine 180 is negative. So we got both positive and negative. Now, anybody else want to chime in here?
I said that it was 0 because the force is perpendicular and the cosine of 90 degrees would be 0.
So force is perpendicular to what?
To the charge.
To the charge.
Like makes a 90-degree angle with the field.
Oh.
That's how I.
So field would be, let's see, field goes something like this, isn't it? Electric field, if I were to draw electric field, it goes from positive to negative like that, right?
Mm-hmm.
And charge makes 90 degree means, you mean displacement of charge?
Just the angle between them.
Oh, just this here
I mean,
and that here 90 degree? Okay, yeah, that kind of makes sense too, yeah. So this line, you looked at it, and field is here, so the angle between them. So this line is just a wire we are using to push it, let's say. Somehow we need to push it, right? Yeah. Okay, now we have case for all three. And I'm pretty sure some of you have more to add on this. Do you want to chime in? How about you? So it looks like nobody wants to chime in. So maybe I like to talk a little bit about it, okay? So work done, in this case, whenever we say work done, we need to ask, work done by what force? It's the force that does the work, okay? So it looks like there are two forces acting based on what you guys said. Electric force pointing down and push force pointing up. This question did not ask the work done by push force or the electric force. It asked about the net force. So what is the net force in this case? Or I should say network. So networks means we can calculate network two different ways. One, find the work done by each of the forces and add them together. Another one, first find the net force and find the work done by net force. So there are two ways we can do it. So in this case, it says it is moving with constant speed. If something is moving with constant speed, what do we know about the force?
Isn't it 0?
Yeah, net force must be 0. So 0 force is doing how much work? 0 work. So that's one way to look at it. Another way, find the work done by electric force and find the work done by push force. And since it is moving with constant velocity, these two forces must be balanced. Okay, so for example, when I'm holding this ball here, what's happening? There is gravitational force on the ball. We call that weight, right? Weight of the ball. And now when I'm holding this ball, I am just countering that weight right now, okay? I'm just applying force equal to the weight. So that's how these two forces are canceling each other. Now, when I make it move, what happens? I'm not applying larger than the weight. It's still same as weight. If I were to use larger than weight force, then this is going to accelerate, because whenever there is net force, there's going to be acceleration. Net force is mass times acceleration, Newton's second law, right? So same idea here. These two forces, push force is countering the electric field force due to electric field or charges, okay? So it's just countering it, so they are equal. So when we move the charge, displacement is same, force is same, but the angle between force and displacement, they are opposite. So it's moving up. So if force is down, so the angle between them is 180 degree. So that means work done by electric force is negative in this case, and work done by push force is positive, because displacement is up, let's say, based on this drawing, and push force is also up. So the angle between them is 0. Okay, and so that means push force is doing positive work, electric force is doing a negative work. So the total work or net work is the sum of those. When we add them, becomes 0 because they are equal in value, and one has positive sign, another one has negative sign. So that's why C is the correct answer in this case. So we reviewed a lot of things here. Newton's law, when object moves with constant velocity, when object accelerates, okay? And we also learned how to calculate work done by force, what work done means. So whenever we say work done, whenever you are asked to find work done, always ask work done by what force, okay? So yes, so in this case, I think C is the best answer, okay? But I can see where A and B are coming from, okay? So work done. So what happens? We do the work. So for example, when I'm doing work by pushing it against the force of gravity, I'm doing work. And by doing that work and making it move higher, what's happening? The height is increasing from the reference point, let's say this table, okay? So what happens now? H increases means gravitational potential energy is increasing. When it comes down, why does it coming down? Because now the gravitational force may be doing work. Yes, of course, both of these forces are doing work simultaneously, whether it's going up or down, but one is doing positive work, gravitational force is doing negative work, right? So when it comes down, what happens? The height decreases means gravitational potential energy decreases. The same idea here for the charge as well. It's the same idea, okay? So let's see if I can move this a little bit. So this is same drawing. So rather than writing D for the displacement, I'm writing delta X, okay? So that's what I'm doing. So when I am pushing this charge, let's say, or when this wire is pushing this charge up, wire is doing a work, just like when you are pulling yourself up, you are doing work, but at the same time, the gravitational force is also doing work, okay? So force by U, and that's the displacement. Both of them, the angle is same, okay? The angle should be 0 between delta X and Fu. So that means you are doing positive work, gravitational force is acting down, and the displacement is up. So the angle between these two, 180 degree, means negative work. So gravitational force is doing negative work, okay? So that's the gravitational potential energy we get depending on whether you are doing work or gravitational force doing work or both of them doing work to change height. As long as there is change in height, there is gravitational potential energy change, okay? So now we use this here. So work done. There is this field. Gravitational force is field. We can write in terms of field, okay? So gravitational force is doing negative work compared to the work you are doing, okay? And they have opposite sign. One is positive, another one is negative. And that change in potential energy of that object can be written in terms of either work done by this external force or U or the gravitational field. But if you calculate work done by using this external force or like U, then what happens? Gravitational change in gravitational potential energy, or in this case, we can simply say even potential energy, equal to that. But if we are calculating work done by the field, means gravitational force, or in this case, electric field, then what happens in that case? The change in potential energy is going to be negative. So for example, if you want to see here, I'm talking about this thing going up, right? So displacement is force you are applying is, like up. So both of them in same direction means theta is 0 degree. Let's say angle between them is 0 degree, means work done is positive. So when height is increasing, what happens? Work done is positive, and that's work done by you. Now, if you are so that work done is same as the change in gravitational potential energy, because height change is, let's say, in this case, it went from down to up. So final is larger than the initial one. So if initial is, let's say, this 1 meter, and final, so initial height is 1 meter, and final height is, let's say, 2 meters, then final 2 meter minus initial. Change in height is final minus initial. So 2 meter minus 1 meter is 1 meter, which is positive. So change in gravitational potential energy is positive. Okay. So the sign of change of gravitational potential energy in this case is same as the work done by you or the external force. Okay. Now, when we look at the work done by gravitational force, as you can see, what happens? The work done is negative. So change in potential must be same. So what happens? It has to be negative of that. So that way change is still positive. Okay, so that's how it works out. I think we talked about this in physics 1 as well. I'm just reviewing that here. So now, how do we apply that one in the electric field case? Okay, so it's the same idea. Work done by E, how do we calculate that? We write force due to electric field, or force due to, yes, electric field, times displacement times the cosine of angle between them. So what is force due to electric field E? We know E is Q times E. So that means in this case, charge is positive. So we can just write Q times E. And by the way, we don't need to worry about positive or negative sign. The sign is given by the angle, okay? So we just write the value of the force. So even if it was negative charge, we would be writing that, same force there. So it becomes QE. So we just use the definition in this point. So when we actually plug in that value of charge, then we're going to be plugging in with the correct sign, okay? Not in the definition of force. If you use the, if you double count that, then they're going to be sign mistake in that case. So in this case, what's happening here? Field is in that direction, means force is also in that direction. Or if we look at in terms of that, we know force is down and this is up. Then what happens here? It becomes cosine 180 degree, because the angle between up, displacement, and force down is 180 degree. Okay, so that means cosine 180 is negative. So here we took account of the sign of this charge by looking at the force on it. Okay, so we know in this case what happens is force is down there, so we did that. So now later when we actually calculate that, then what do? We just plug in, depending on whether it's a positive or negative, we just want to plug in that. Okay, so we are using the quantities, two different ways here. One is vector, so we are treating it as a vector. So what we are doing is, when we are using force, we are drawing the force for the direction, okay, and determining the angle. So we are drawing it, not using the sign of the force there. We are just drawing the arrow. That's what we are using for the sign of the force, okay? So keep that in mind. Okay, so that's that. Then what happens? This is negative because cosine 180 is negative. So that's the work done by the electric field. Now, what is the change in potential energy? Work done by field and change in potential energy, they are related through, let's forget about the external force for now. We are just talking about work done by field at this moment. They have opposite sign, okay? So whatever work done you find, you change the sign. So if this is negative right now, you make it positive, okay? So that's going to be the change. Okay, so I just left with the question. So that means change is going to be just QE delta X, okay? So that's going to be the change in potential energy due to this electric field when charge is moving up, just like this, okay? So now here is this question. So this is past question on the let's say the electric potential. So let's work together here. So we have positively charged plate and there is negatively charged plate, right? And now what we have is negative charge. So we had positive charge in the last example. Now we have negative charge. Okay, so how the situation gonna change? Okay, so now it says draw the direction of electric field between two parallel charged plate. What's the direction of electric field? Is it still same or is it up? What do you think? We are talking about electric field, not force here. So electric field depends on just the source charges. It does not depend on this test charge. So the charge that's moving, we can think of that as a test charge, okay? So field does not depend on source charge. So no matter what we have here or we don't have here, field is always pointing from positive to negative, okay? Just like we learned in the last chapter. So that's what I'm drawing here. Draw the direction of electric field between two parallel plate charge. So now, what is the direction of force on the negative charge? So force depends on both charges. Force comes from both charges, not just the source charge, okay? So, can you draw the force on the negative charge here? Please go ahead and draw it, okay? Did you draw it? So there are two ways you can look at it. One, just look in terms of charges. So there is negative charge and this is negative charge. So that means it's going to get pushed or going to get pulled by this. We can just find the direction of force from just the properties of charges. That's one way to look at it. Another way, force on the positive charge is in the direction of field and negative charge is in the opposite direction. Okay, so that means force in this case is in that direction. Force due to electric field is in that direction. So F is force I'm representing F to represent force, and I'm writing subscript E to represent that the force is due to electric force. It's not gravitational force, okay? So did it match what you drew? Okay, I'm hoping you guys are participating, okay? So this thing gets fuzzy and confusing unless you practice it. So that's why I'm going so slow. A little later, once this thing becomes a bit clear, I'm gonna go a bit faster, okay? So now, what is the work done by electric force on the charge? So how do we calculate that? Work done by electric force. What is the definition of work done? Force. In this case, electric force. So that's the same force here, Fe times d. Displacement means, in this case, I'm writing delta x. So let me write that down as a delta x. And cosine of angle between them. So in this case, displacement is up. Did it say? Yeah, looks like I didn't show the direction of displacement. Let's assume it is same as what we had in the previous slide, okay? So that means force and displacement, they are in same direction, means the angle between them is 0 degree. So cosine 0 is positive 1, right?
I'm sorry, 1 second. So you base the direction off of the charge, not like the electric field?
So displacement, somehow, let's say this thing is moving in this direction there, okay? Just like last time I was just pushing it, right? This time I'm not pushing or pulling, so it is free to move. Then which way is going to move? We know it's going to move in that direction, right? So now, to write the work done, I need to write formula. Let me write down just the cosine and angle here. Angle what? Angle between force and the displacement. So what I was talking about was that this angle comes from electric force and displacement. So force is pointing this way and displacement is also in the same direction. So the angle between them is 0. So it depends on the force. Remember, the work done comes from the force, not from the field. I think that was your question. Okay. Okay. So now, okay, so I can write this as Fe delta x, and then cosine 0 is 1, so that means it's a positive. So now what is change in potential then? It's going to be negative of work done. So that means negative and work done is this. So that means it is Fe delta x. Okay. So now, when we write this force in terms of charge, we're going to be just writing Fe is Q times E. We're not going to be writing negative E here because we already took care of that direction negative sign by putting that, okay? So we do not want to double count that negativity. This force direction, this came because this charge is negative, okay? So now if I plug in that charge negative here, we are double counting. We do not want to do that, okay? So that's the change in electric potential energy. So now we learn that the electric field, so we can write this in terms of that negative, and in this case, charge is just E, and the field is E, and displacement is delta x. Okay, so that's the change in potential energy. And now, since this is the source of uniform electric field from two plates. We learned that in the last chapter that this can be written something like this. And see, this E here came from the test charge that's moving, right? And this Q is the source charge on the plate. So keep that in mind. So we can plug in that thingy and write the formula. So for example, it's going to be negative E times, oh, I need to replace that E by this Q epsilon naught times A, and then that's E. Now what's remaining? Delta X. Okay, so we took care of sign. All we need to do is just plug in the values in this case. So for example, we may have question like this. What is the change in potential energy? Means delta U we are looking for. So that means that's what we are looking for. Okay, of a proton. Okay, of a proton when it moves 2 centimeters. Assume that each square-shaped plate has a side length of 1 centimeter. So why do we need this information here? That's for the area. This A is the area of the plate. So we can get area from there. And source charge is this. It's in microcoulomb. So we want to write that as a 8.85 times 10 to the power negative 6 coulomb, right? So now, how do you change that? So if it was a negative charge, you will just plug in the value of negative charge there, just value of negative charge, because the negativeness already came from there, or from this force there. But now we are talking about proton, which has positive charge. So what we need to do is to replace that. One way we can do it is go back to the previous slide, and that's what we did, right? So it was like positive and the force was acting down, that means, okay. And now, what is the change in potential energy of a proton when it moves 2 centimeters? So in this case, it does not say it's being pushed by something. It's just moving. So that means it is freely moving because of the electric field. So we are not told which way it's moving, but we can figure that out, which way it is moving. It's not being pushed or pulled, right? We are just putting positive charge there. So which way it's going to move then? It's going to move this way. Positive charge is going to move this way. Okay, so what happens in this case? So displacement is in that direction, field and force is also in same direction. So the angle between them is 0 degree. So that means work done gonna be what? Work done gonna be, we can go back here, write force times displacement and cosine of angle between them. So force Fe and delta x, and what's the angle between them in that case? Again, 0 degree. Remember, last slide versus this slide, what's the difference? Last slide, we were pushing it so that it's moving up. It was moving up. Right now, we're not pushing it. We are just putting it there and letting it move, just like this. Go back to the gravity, which is here, we can easily see. So last time we were pushing it, so it was moving opposite to the field. Now what's happening? We are just letting it go. So that means it's gonna just go down in the direction of field. So that's a displacement, okay? And what is force here? It's the electric force that's in action. So that's force. Force is down, displacement is down, so the angle between them is 0 degree, okay? So now, once we take care of that, what happens? We can just plug in the value of charge that way. So this becomes positive, okay? So now change in potential going to be opposite of the work done, means it's going to be negative now, okay? So what happens here? We get negative, and what's the charge of the value of the charge of a proton? Same as the charge of the electron, only sign is different, okay? So what happens? It's going to be same. So basically, you can just plug in numbers. So it looks like it's going to pick up that negative sign, and you're going to get the answer. You just plug in those. So area in this case, we know it's a square. So area of a square is square of the length, right? Length times width. But when length and width are same, we can say length is square or width is square. So in this case, it's in centimeter, so you need to convert that into meters. Similarly, the displacement delta x is in centimeter, so you need to convert that into meters to get the correct answer. And potential energy, its unit is in joule, okay? Joule is same as Newton times meter. So that's how you do the calculation. So basically, you're gonna be just plugging in these numbers right there, these numbers over there, and getting the answer. So this epsilon naught is a constant. It is, I think, 8.85 times 10 to the power negative 12. So that's epsilon naught. Area is this, okay? Delta x, Q is given. So that's how we take care of potential energy. Okay, so that's one way to look at it, by drawing the diagram and, you know, the force, displacement, and use the definition of work done and so on. So later, pretty soon, we're going to be talking about or writing the equation for the electric potential energy, and we'll learn how to use that formula, okay? But before we do that, there is a question directly related to what we just talked about, okay? So external force is not shown. Oh, wrong place. It's not shown here. Is making the charge move with constant velocity. So field, like a gravitational field, if there is no external force, if there is no my hand there, what happens? Field makes it accelerate. But if it is moving with constant velocity this way or that way, that means external force is in action, okay? So that's what it's talking about, the external force. And I think that's the agent here, that's the external force, okay? That external force is agent here. And it's making charge move with constant velocity. The work done by the agent and done by the electric field, that's the work done by electric field, and done by the net force, okay? And that's that. So there are three, and you are asked to find sign or the value, okay? And situation is this. So there is this positive charge, positive plate, negative plate, and this is positive charge we're talking about, that's moving, okay? And it's moving with constant velocity. And looks like, based on this arrow, it is moving in that direction, okay? So those informations are there. You don't need to do math here, but you need to draw the direction of force and displacement and so on to find the work done correctly. Okay, so let's do that. And I'm giving you for this, let's say 1 minute and 30 seconds. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So net force, constant velocity means net force must be 0. So the work done must be 0. So these two are the possible answer. These are not. Okay. And now, which one is the correct answer? So agent and field. So field, this is positive charge, so the force due to field, Fe, gonna be in this direction, in the direction of field. So field and the force due to field and the displacement, they are in same direction, means the theta is 0. So that means the work done gonna be positive. So agent is doing positive work. Okay, agent is positive work. Oh, not agent, field is doing positive work, sorry about that. Field is doing positive work, right? Because the force field is pointing in that direction. So agent, which way it's acting, must be acting this way, otherwise it would just accelerate. But the question says it's moving with constant velocity. So external force or the agent is acting this way. So force and displacement opposite direction means the work done is negative. So that makes sense. So that's why C is the correct answer in this case. Let's see what happened. Yeah, most of us got it right. Good job, folks. Okay, so it's a break time. So let's take a break. But if you like to ask something or talk about something here, feel free to do that. Okay, I'm gonna take short break as well. Okay, folks, let's get back. So we are talking about potential energy, and we learn how to calculate potential energy of a charge when it is moving in an electric field. Okay, so it could be moving freely just because of the electric field, or it could be moving influence of external force and the electric field. So we learn how to calculate change in potential energy. So now what we're going to do is we're going to be writing the equation that allows us to write down the potential energy between two charges. Okay, so what happens, let's say if one charge, let's say this is source charge and this is test charge. Okay, if it is sitting there, we can think of something like let's say it wasn't there. Now what happens, it was moved, it was forced to move to come to that distance. Now it's sitting there. So the separation distance between these two right now is r. What is the potential energy between these two charges then? Okay, so that's what we want to calculate. So there is, let's say, the source charge, I'm denoting that by q, and there is this test charge, I'm denoting that by lowercase q. So it's sitting at the distance r. So we already know how to find force between these two charges, k, q, q, r square, right? So that's just the magnitude of the force. So let's use it as it is, okay? Draw action, how to take care of draw action, we'll talk about that pretty soon, okay? So now, what happens? As distance change, force change. So to use the concept of potential energy, we need work done. So that means we need to assume that it was somewhere far and then it was moved to that place. So somebody had to do work to move it to that place, and because of that, that work was transferred as energy on this charge. Okay, so that's what we're going to be using. Okay, but work done, we learn how to calculate work done is force times displacement. In this case, force is kind of changing with displacement. So the way I'm going to be writing here, not going to be, let's say, 100% theoretically correct, but practically it works out. So if we want 100% theoretically correct way of coming up with the equation, we need to use calculus. We don't use calculus in this course, so I'm going to be just writing tentative idea how it works. Okay, so this is what I'm saying. Okay, it was at very, very far distance. Initial distance was infinity, let's say very far, and then at that point what happens, the force is 0 at that point. Why? Because r very large, infinity, means force is 0, right? When we divide something by very large number, what's the result? Close to 0. So when it's infinity, then it's 0. Okay, so in this case, what does it mean actually infinity means? What is, what does infinity means in this case? So there is one charge and there is another charge. So infinite distance in this case is not actually billions of kilometers. No, it's not. So as long as this charge, test charge, does not experience any force, right? That's the infinite distance for this. So charge, it's hard to see, okay, but magnet, I'm pretty sure you have played with magnet, right? So you have a magnet, and what happens is that when you bring something close to a magnet, then it experiences force. For example, I have this pen, and let's see if you can see my tablet and pen. So I have this pen and tablet. What happens up to this distance, this pen is not feeling any force, but when it comes, let's say, oh, there, see, it gets snapped. So the distance when it's not feeling any force, that can be counted as an infinite distance. So for practical purpose in this kind of situation, it could be just few centimeters. Okay, it doesn't have to be kilometers, billions of kilometers. Infinity doesn't have to be infinite kilometers. So it could be any value depending on situation. So that's what it means. Okay, so let's suppose it was really far. So in that case, what happens? Force is 0. So whenever force is 0 means distance is very large, other way around. Okay, so that means if force is 0, that means you don't need to do any work to move it. Okay, you don't need to do any work if external force doesn't have to do any work. So that means at that point potential energy going to be 0. So at infinite distance, at large distance from the source, the potential energy going to be 0 for any charge. So that's what it is writing. Okay, so we take that as a reference point. So for example, in case of gravitational potential energy, we kind of used some height, wherever we chose height as a 0, we use that as a reference point. Okay, so if it was tabletop, we chose that height 0 and measured height from there. Okay, so in this case it works slightly differently. The far point, we take that as a 0. Okay, at infinite distance we take that as a 0. Okay, or large distance. So that's what we do. Okay, so now when this is at a particular distance and it starts experiencing that force, snapping force, right? So that means to move that away, you need to do work, or that force is now doing work. So we can calculate work done as force time whatever distance it moves, and replace force by this equation, force equation here. Okay, and displacement as r, and force changes with the r, and r is changing when you are moving closer and closer. Okay, but here I'm taking a little bit shortcut, and let's say that cancels, giving me this as the equation for the work done. Okay, this as the work done. So now change in potential energy is negative of work done. That means we can write this something like this here. Change in potential means final potential and initial potential. Okay, so if we started moving it from the infinite distance, we can think of initial potential as a 0. Okay, and here it was negative, and I did not put negative sign here. So now what's going on? How do we use it? So it turns out, if like let's say this is positive charge, if this is positive charge, then, and this is also positive charge, force going to be pointing this way, right? And the field going to be also, let's see, yes, field going to be pointing away from the positive charge, means it's going to be in the same direction. If both of them are positive, then work done going to be positive there. But if it is negative, then work done going to be negative, right? But in this case, when I write something like this, now I don't need to go back and look all those history. It makes a bit easier if we just keep track of those signs here. What is the sign of Q? What is the sign of Q? You don't ignore that, but keep track of those. While using this formula, keep track of sign. So what you do is, to force calculation, Q1, Q2 over R square, K, what we did was we did not keep track of sign. We just plug in the number, and sign we use like positive charges, like charges repel, and opposite charges attract, right? So that's what we used. Now, in this case, what do is we keep track of sign. So that means plug the signs as well. So that's how you want to use this formula. So this is the potential energy. So this difference is change in potential energy. And if it began with 0 potential energy, change in potential energy is going to be same as the final potential energy. Okay. And I think I talked about the sign. So we can just write the, potential energy, something like that, and just plug in the right sign. Okay. So that's how we're going to be using. So the potential energy is given by K times source charge times the test charge and R. So just like force is always between two charges, similarly potential energy is between two charges. It has both charges in the equation. Keep that in mind. Later we'll define potential. So like field has only one charge. Similarly, potential, we're going to be defining potential so that we're going to be writing formula in terms of source charge only. So there is difference between potential and potential energy. So potential energy has both, it has both charges in the formula. And now, how is this different from force? Force has, see, it is like a force, but force has R squared, distance squared. But the potential has just R, not R squared. That's the difference there. They look very similar, but there is slight difference, okay? And they are related to each other, of course, okay? So now let's take a look at this problem, how we can use it. So now, when we're talking about force and field, remember, they being vector, we had to draw the arrows and then add them correctly using the vector addition method. Oh, potential energy, scalar. We don't need to draw those arrows. They are scalar. Just write number with the sign. That's it. Okay. So let's see. I can make it show it here. So what is the potential energy if Q means this has a value, has a value of 2 coulomb. Okay, I'm keeping things simple here, giving, all of the charges may not be so much realistic. I'm keeping this, reasonable so that we can do the computation bit reasonably or bit easily. Okay, so 2 charges, one is 2 coulomb, one is 1 coulomb. And the distance between them is 9 centimeter. Oh, it's not in meter. So we need to convert that. So R is 9 centimeter means 9 times 10 to the power negative 2 meters or 0.09 meters. It's the same thing. Okay. So now it says, what is the potential energy? So what did we learn about potential energy? So potential energy is K, Q, both charges, over R. So we know all of these. K is 9 times 10 to the power 9. Okay. And then Q is 2 coulomb. Nice. I don't need to convert that to coulomb. It's in coulomb. And then small q is 1. Right? And then R is that 9 centimeter means 9 times 10 to the power 2. And everything, once we write in SI, this being energy is going to have a unit joule. Okay, so unit conversion is a bit little difficult in electricity especially, okay? So if you can keep track of those, you should be fine, okay? So that's the potential energy. So in this case, both charges were positive. So I just used the positive number. That's good, okay? So now if one of that was, let's say, -1 coulomb, then I need to use that as a -1 coulomb, okay? If it was negative, then I'll put that negative sign there. Keep that in mind. So this is just the potential energy between two charges. Now, what if we have more than two charges? How do we do it? So there is this charge here, there is this charge, and there is this charge, so three charges. So that means, let's say, we can think of, we had to do work to bring this charge close to this, and we had to move this charge, close to this, and so on. So what happens is there are going to be this combination of all of these, and there is potential energy between these two as well, okay? So in this case, we don't need to draw arrows. That's good news. Rather, what we do is we write the potential energy. See how we had K times charge. So K, so for each of the pair, they're going to be K. So I'm factoring K out. And now Q1, Q2 means I'm calculating potential energy between these two first. That's what that is. And distance between charge number 1 and charge number 2 are 1, 2, just a notation, right? And similarly, between Q2 and Q3, that comes from this. And now from Q1 and, is that Q3? Yes. So Q1 and Q3 coming from those three pairs. So that's how you write the all possible combination. And now it's just a matter of plugging in the values with the sign, okay, with the sign. So here the answer, I have written the answer, but for example, there is Q1, there is Q2, so I'll just write the first term here. So this K being 9 times 10 to the power 9, you can do that. First term, how do I write it? Q1 times Q2. Q1 is in microcoulomb, so I need to convert that into coulomb. How? Multiply that by -6, okay, coulomb. So that means in this formula, the Q1 is positive, but yes, so I don't need to worry about that negative sign there. So that's the Q1, okay, that's Q1. Now, how about Q2? Q2 is 6.5. but it's negative, so you want to include that negative there, right there. Okay, so that's Q1 and that's Q2, and over the distance between them, separation distance between them, that's 12 centimeter, means 12 times 10 to the power -2 meter. So this is just one term, so we need to keep adding other terms and then punch in the calculator. Okay, so that's how it is used, this formula is used. Okay, so now, just like we started from the electric force in the previous chapter, and then we went to the electric field, defining that is the force experienced by the unit charge, per unit charge. So we divided force by the charge, one test charge, okay? And then that charge got canceled and we had just one charge in the equation. So now we are doing the same thing here, okay? So potential, we define that as a potential energy divided by, let's say, the test charge. Now, potential, we already know it. Potential energy, we already know it. Its unit is joule. So that means unit of potential gonna be joule per coulomb. And that's what the volt is, or voltage we are familiar with, okay? So battery, for example, when it says 1.5 volts, it's talking about the potential difference between two terminals of the battery. Okay, so potential at a point and potential difference. So we'll talk about difference pretty soon. So what we do is just one thing here. So unit volts, we denote that by uppercase V as well. Maybe when we write volts, we write lowercase v, not the uppercase. Sorry about that. But when we just write V as a volt, just like joule, J, uppercase J, coulomb, uppercase C, we do the same thing for the volts. And we do not potential by the V as well, so uppercase V. So could be confusing. As long as we can keep track of things, we should be fine, okay? So there is source charge, and now there can be potential. Just like source charge, and there can be field at any point around that source charge. Similarly, now we can talk in terms of potential. So what are we doing here? So when we are talking in terms of electric field, we are talking in terms of vector quantity, vector field, okay? So when we are talking about potential, we are talking about in terms of scalar. That's it, okay? So if there is this charge, so what's the potential here? We don't need charge here for the potential to be there. Its potential is still there, okay? So when we bring charge over there, then it feels the energy. So we say, okay, this charge has a potential energy at that point. But all we need is source charge, and the formula gonna be, where is the formula for the potential? Looks like I did not write it. So our potential energy was KQQ over R. So that was the potential energy, right? So now, what is the potential then? Potential is just potential energy divided by this charge, means this charge is gonna go away for the potential. So that's the formula. Okay, so that's the formula for the potential. So here, potential energy can be written as Q times V, okay? And we already know, I think I'm writing formula like this rather than that, okay? So what happens? That's the potential energy, and I'm copying that. So that way you can see this Q is being canceled, so that gives you potential, okay? So that's the formula for potential. Another way to write it, okay? You can write from this definition like this or like this. So what we have here, just R and just one source charge. No test charge in this formula. So we are making test charge independent. By defining potential, we are making it test charge independent. Just like by defining field, we made it test charge independent. We are doing the same thing. The difference, one is vector, another one is scalar. So do you guys know what is the electric field at this point? If for this source charge, if I were to write electric field, I can do that. It's going to be KQ, KQ, but rather than R, it's going to be R squared. Only that's the difference, okay? See how closely they are related? By one R. Here, there is just R. Over here, it's R squared. So R versus R squared. That's the difference, okay? So yes, they look very similar, could be confusing. Hopefully you are getting what's the difference here. And what's the advantage? Because the potential being scalar, easier to handle. So that's why you see everything written in terms of voltage, not in terms of Newton per coulomb, not in terms of field, okay? For our practical daily life, it's in terms of voltage. What's the voltage of this battery? What's the voltage of the outlet? 120 volts. So that's the potential difference between two plugs, plug hole. Okay, that's what that is. So change in potential is change in energy divided by Q. So that's the potential difference. Change in potential means potential difference. Okay. So we can write something like this. So we can go this way or that way. So for example, if we know potential energy, we can find potential. If we know potential, we can find the potential energy. They are related through just Q. One Q, just that's the relation, okay? Or this one here, okay? Just one Q between them, okay? Just like between force and field, we had just one Q. You see that? Just the resemblance here. So we are learning how to describe the same kind of thing, similar kind of thing in terms of the scalar quantities. Just like in physics 1, we learn how to describe in terms of Newton's laws and use kinematics to solve problem. And then later we learn how to use conservation of energy to solve problems. And using conservation of energy in some cases was easier than using the kinematic equation and the Newton's laws. Same idea here. Now we're going to be using conservation of energy to solve some of these problems. Okay, where one energy going to be now electric potential energy. We had gravitational potential energy, we had elastic potential energy. Now we have one more potential energy, which is electric potential energy. Okay, so now, yes, we use that, and we have made several devices, ECG display, for example. Remember we talked about EKG last chapter, where it was the actual, the electric field. In terms of electric field, we talked about how the field of the dipole changed and the display goes like that. So now we can talk in terms of potential as well. Okay, so that's that. So if it's a regular, yes, this is physics. So I don't teach medicine here. I don't have training on medicine, of course. But as far as I know in terms of theory, so this one, that one, all these, they are repeating. As long as they are following the same pattern, that's the normal. Now, if the pattern changes, that means it's abnormal. Now, the pattern could be changing differently because of the different reasons. And that's where medical degree comes in handy, okay? So anyway, what do you see? 1 volt. See, we are measuring the potential there. Okay. So now here is question for you. You have 1 minute and 30 seconds to answer this question. Thirty more seconds, folks. 5 more seconds. 5, 4, 3, 2, 1, and it stops. So we mostly got A, and I think that is correct answer. So why is that? Because field is a vector. So at this point we assume there is a test positive charge, so that means that's going to be field due to that charge is going to be that, and field due to this charge is going to be pointing that way. They are pointing in opposite direction, and they have same value because they are equal distance. Midpoint means equal distance, right? So distance is same, this charge is same, this charge is same. So electric field being kq over r square, what happens? The value going to be same because q is same, r is same for both charges at this point. Okay, so the difference is one is pointing this way, another pointing that way. So one is canceling the another one. So net becomes 0. So if we assign this as a positive, then this is going to be negative. Remember, field is a vector. So now the potential. How about potential? So potential we know is given by kq over r. And now it does not have direction, but we need to plug in the correct value of q. And both of these are positive. So that means it's going to be kq over r from one and kq over r from another one. So there is no cancellation. Okay. So that's why it becomes non-zero. Okay. Good job, folks. So little confusion there from some of you. Hopefully it explains it. Okay. Anybody likes to add anything on this one here? Okay, maybe not. So now we see there are batteries that may be like 9 volt. For example, in smoke detector, in smoke detectors, it uses like 9 volts. Okay, and regular dry cell, they are 1.5 volts. So what does it mean when we say, okay, it's a 9 volt battery? Let's talk a little bit about it. Okay, so for that, so potential difference between these two terminals. So what it means is the potential difference between one terminal and another terminal of the battery is 9 volt. So one terminal is negatively charged in a battery, another one is positively charged. So potential here can be negative potential and potential here can be positive. But usually for convenience, what we do is potential being just the, like just a scalar number, we can scale it. So if it is, let's say -5, let's see, we can say it is -4.5 here and +4.5. So the potential difference is going to be 9. See, difference is final minus initial. So when we are taking difference, we need to subtract. And when we are subtracting negative number, it gets added. So because of that, it's 9 volt. But we can also say this is 0 and this is 9 volt. Okay, one terminal, one side at 0, another one is at 9 volt. It's being scalar, we can scale by a same amount of number. So by doing that, what are we doing is we are going from -4 to 0 means we are adding +4.5 here, means we need to add +4.5 here as well. That becomes 9. So there are different ways. Okay, so now if a 9 volt battery lights 12 watt bulb, how many electrons are flowing through the bulb? So when we talk in terms of field, we say, okay, the charges are moving in a field. Now we can talk in terms of a potential. So in this case, it says it's a 9 volt battery and it's lighting up 12 watt bulb. How many electrons are flowing through the bulb each second? number of electron every second. So that's what we want to know in this case, okay? Oh, so how do we do it? Once we learn about Ohm's law, it gets even easier. But since we haven't done Ohm's law, we need to think in terms of power and energy and the potential. Okay, so that's what we need to think in terms of. So when we say 12 watt, what it means? Watt means joule per second. Remember we learned in physics 1, power is rate of flow of energy, rate of change of energy. Here, what energy is changing? Electric energy. So this is the rate of change of electric energy. So that's what that is. So we can also write that as a joule per second. So change in energy, electric energy over time is 12 joule per second. So that's what we know. Now, what is change in energy? And there is potential there. Do we know the relationship between potential energy and potential? Yes, we do. So potential energy is Q times delta V, right? So we can use that here, Q times delta V. So Q is the charge, the total amount of charge that's flowing here, okay? And over delta T. So it's flowing through the ball each second means time is basically 1 second, it's known, right? So this is not 9, but it is Q, okay? It is Q times delta V is 12 joule per second. So since we are talking about per second, so we can replace this by 1 second. And delta V, potential difference is 9 volt, okay? So Q times 9 volt. Hopefully you don't get confused from my writing here. Q times 9 volt divided by 1 second is equal to 12 joule. Okay, so now, are you talking to me? Maybe not. Okay, so what do we want? It says how many electrons. So it's the electrons that's giving the charge. Okay, if there is 1 electron, we know exactly how much charge is there. Now we know the charge. If we know, is there a way of?
Sure, it's fine. She said it's good.
Let's enjoy the moment,
So
okay?
you can come.
Family moment. Meantime, I'll just write down some numbers here, solve the equation here. The Q
I lied.
Okay. So now this is charge, total charge. That's the total charge that's flowing. Now how many electrons are there? So total charge can be written as number of electron. Oh, by the way, charge per second. Or what I can do is I can do this. This was joule per second. What happened here? Joule per second. So the second and second cancels. I can now write just charge that. And Q is N times E. Number of electrons times E. Remember, when current is flowing through the wire, means it's the electrons that's moving. Okay, in a solid, it's the charge that's moving, means electrons that's moving. So that means I can write N times E, and this is going to be 12 over 9. So now what is number then? It's going to be 12 over 9, and now this E goes there. Not Q, but 9E. So 12 times 9 times 1.6, 10 to the power negative 19. So that's the value of E, right? So we have a number, so that means that's how many electrons are flowing. It's a lot. Trillions of electrons are flowing per second in a wire when you connect it to 9-volt battery. So that's what it is saying. Okay, so that's how we can use it. So this makes you use the relationship between potential energy and the potential. Okay, and I think there is one more question here. So it says, what is the potential difference between two parallel plates separated by a distance? And it says, assume charge in area of each plate Q and A. So there is charge Q and the plate has an area A. And the question is, what is the potential difference between two parallel plates? And the separation distance is D. Okay, so we are looking for a potential difference between these two. So how do we do that? So we can find potential at one point and then potentially at another point and then find the difference. That's one way to do it, right? Or we can go from electric field. Did we learn the relationship between that? Probably we did not. So let's go with the in terms of potentials, okay, not the field. So potential difference can be written as a potential energy per unit charge. So we can just use, what is potential energy? Force times displacement. And now, oh, there is field. Now we know field is, in this kind of situation, it is Q over epsilon naught times A. So we can use that. So here, before we use that, we can cancel that, and E and delta X is just D, okay? And so now E can be found from this charge in A. We've been using that Q over epsilon naught times A, right? So that means we know everything here, means we can find the potential difference. So basically, this also gives you the relationship between potential difference and the electric field. We didn't know, but now we derived it. So just divide multiply electric field by the separation distance, and that's going to give you potential difference. Or bring this d and divide, that's going to give you field. So that's another important formula we have here, okay? Oh, okay, so folks, I think we're going to be just leaving it here, okay? If you have quick question, feel free to ask, or else I'm going to be ending this meeting.
Thank you.
Thank you, guys. See you Wednesday.
And thank you, Professor.
Okay. Anybody has a question, or else I'm going to be ending this meeting. So please come forward. If not, okay. So question, Elena?
Yeah, so you host office hours today at 4:30, is that correct?
Yes. Is
Would
that
that just be the
4:30?
same Zoom call? I
Oh,
think that's what it said on the syllabus.
Okay, 4:30. Okay, so today 4:30. Yes, it's the same Zoom. Yes, this Zoom. Okay.
Awesome, thank you.